let us focus on the net rate of work done, that is the integral energy balance equation. We have discussed we applied the transient term, the convection term on the left hand side for the small control volume, and we also discussed how to express the net rate of heat input term for the small control volume. So, now we will focus on the net rate of work done term on the right hand side of the integral energy balance equation, and let us see how do we apply that for the small control volume. Okay. So, if we recall our discussion on this net rate of work done, when we discuss integral energy balance equation, we split the work done in terms of shaft work and then work done by pressure, work done by viscous stresses, of course all in terms of rate. Now, let us see what are the terms we are going to take forward. First, our control volume, I am using this both sometimes as a domain, sometimes as a control volume. Let us say this is our domain, our control volume is somewhere inside, so and there is no shaft there. So, within the small control volume we do not have a shaft, and so the shaft work is 0. Now, when we discuss the integral energy balance, we neglected the work done by the viscous stresses. Similarly, here also we are going to neglect the work done by viscous stresses. Now, is it justified? When is it significant? Okay. It is significant when, let us say you have a very viscous fluid flowing between, let us say, two parallel plates, the distance is very small, and let us say the top plate is moving at a very high velocity, which means that the velocity gradient will be very large. So, in such conditions the work done by viscous stresses will be significant. So, the work done by viscous stresses is significant when you have a very high velocity gradient and your fluid is viscous, and most of the cases, almost most of the times this is not significant, and so we are going to neglect that. So, there is no shaft work and we are going to neglect the work done by the viscous stresses, and we are going to consider the work done by the pressure forces only. Though we had split work into 3 terms, shaft work is not at all there, viscous work done by viscous stresses we are neglecting it, okay, we are neglecting it, and we are going to consider only the work done by pressure forces. Now, when we derived the integral form of energy balance equation, the rate of work done by pressure force was expressed by this integral expression. To quickly recall, the rate of work done is equal to dot product of the force into the velocity. The force due to pressure is P into dA. So, let us write down that P into dA, and we discussed that the direction of pressure and the outward normal are opposite each other. So, along with direction, the force due to pressure is represented by this minus P dA n vector, and then to get the rate of work we dot it with the velocity vector, and this is for a small area. To get for the entire control surface we integrate over the control surface. So, the rate of work done by pressure is given by this integral expression minus P v dot n dA integrated over the control surface. This is a recall slide. If we recall this, it will be easier for us to understand the next few slides. What is that we are going to do in the next few slides? We are going to apply this expression for our small control volume, in fact for the control surfaces. what is that we discussed in this slide is that this was discussed when we discussed the integral energy balance equation. We applied this equation for the inlet for flow through a pipe and the outlet of flow through a pipe. At the inlet what happens, V dot n is negative. So, this integral term will be positive, and work done is positive means that work is done on the contents of the control volume by the pressure force. So, positive or negative is with respect to the fluid. So, when we say work is positive, work is done on the fluid by the pressure. Here written as work is done on the contents of the control volume, which is a fluid, by the pressure force. And at the outlet, V dot n is positive, and so the rate of work done term is negative. And what does it mean? When you say negative, work is done by the fluid against the pressure force, and this is what is written here as work is done by the contents of the control volume on pressure force. So, to quickly recall, we applied this for flow through a pipe. At the inlet, V dot n is negative, rate of work done is positive, which means that work is done on the fluid. At the exit, V dot n is positive, rate of work done is negative, which means the work is done by the fluid. Okay. So, now if we recall this, it will be easier to understand these slides. Now, before proceeding further, let us understand the two control volumes shown here. The left hand side control volume, the force due to pressure is shown. Pressure is a compressive force, that is why all the arrow marks are facing towards each other. For example, on the left face the force is towards the positive x axis, on the right face the force is towards the negative x axis. Okay. We have seen that several times, and P evaluated at x and P evaluated at x plus delta x, correspondingly all other directions. Okay. So, the left hand side control volume is we are familiar with, we have discussed that during the derivation of the differential momentum balance equation. Now, let us move on to the control volume on the right. What has been done is that all the pressure terms has been multiplied with the velocity in the respective directions. Let us take an example. In the left face we had P into delta y delta z, it has been multiplied by Vx. Similarly, on the right face we had P into delta y delta z, we have multiplied by Vx, and similarly in the y direction Pvy here, Pvy here, and then z direction Pvz and then Pvz. So, the pressure has been multiplied by the velocity in the respective directions. Now, what does it mean? What does these terms mean? Okay. So, let us take this term once again. Pressure is force per unit area, you are multiplying with the area over which it acts, and hence you get the force, multiply by the velocity, we get the rate of work. So, all the terms in the control volume on the right hand side represent rate of work done. Okay. It could be either on the fluid or by the fluid, but all of them represents rate of work done by pressure force. Okay. So, quickly to recall, pressure is force per area, multiplying by area you get force, you multiply by velocity we get rate of work done. Okay. And so, all the terms represent rate of work done, could be on the fluid or by the fluid, and that is what we are going to discuss now. Okay. Now, let us take the x direction and write down expression for rate of work done by pressure force in the x direction. Okay. Now, at the left face the pressure or force due to pressure is along the positive x axis. Velocity is also along the positive x axis, always Vx is along the positive x axis. So, at the left face pressure is along positive x axis, velocity is also along positive x axis. That is why this line says at the left face P and Vx are in the same direction. Now, when a force is along the positive x axis, it does positive work. Force in positive x direction does positive work. What is positive work? Positive or negative work is with respect to the fluid. So, when we say positive work, work is done on the fluid, So, at this phase, at the x phase, positive work, what is that work? P V x at x into delta by delta z, that work is done by pressure force on the fluid in control volume. To be more formally, it is rate of work done by pressure force on the fluid in the control volume. Now, other way of explaining is that we have seen this expression in the last slide for the rate of work done by pressure force. Let us apply that for the left face. We have minus P here, and V dot n, because it is inlet phase, becomes minus Vx multiplied by area. And so, when you, how do you write it formally? It is P Vx evaluated at x delta by delta z, and that is positive, which means that work is done on the fluid. Other quick way of explaining is that we have force due to pressure along positive x axis, velocity also along positive x axis, and then we know that rate of work is dot product of these two terms, and because they are along the same direction, we get P into Vx. So, all are equivalent ways of explaining this term. So, to summarize this slide, when you multiply P with the velocity in the respective direction, you get the rate of work done. We have taken the left face and seen that it represents the rate of work done by the pressure force on the fluid in the control volume. That is why we discussed this pipe. So, this inlet and this face are analogous. So, now let us go to the right hand side face and find out the rate of work done by pressure force in the x direction. Now, right hand side face, what happens? The pressure is along negative x axis, velocity as usual is along the positive x axis. Now, that is what is written here. At the right face, P and Vx are in opposite direction. So, pressure along negative x axis, velocity along positive x axis. Now, a force in negative x direction does negative work. Force due to pressure in the negative direction does negative work, and so this term on the right hand side, P Vx evaluated x plus delta x delta y delta z, represents negative work. What is negative work? It is work done by the fluid on the pressure, or we say work done by the fluid against the pressure. Okay. So, the right hand side we have, if you want to take into account the sign, then it is with minus, otherwise P Vx evaluated x plus delta x delta y delta z represents the rate of work done by the fluid against the pressure force. Okay. So, once again we can use the expression which I have written in the previous slide. We have minus P here. Now, V dot n is positive because it is outflow, and hence we have Vx here multiplied by area. How do you write formally? It is minus P Vx evaluated x plus delta x into delta y delta z. Okay. And other way is, of course, the force due to pressure is along negative x axis, velocity along positive x axis. So, if you take a dot product, you will get minus PVx evaluated x plus delta x delta y delta z. Okay. So, once again 3 ways of explaining. Summary from this slide is the term here represents rate of work done by the fluid against the pressure, and that is analogous to the outlet of the pipe. That is why we discussed the flow through pipe before discussing these 2 slides. Okay. So, now let us find out the net rate of work done by pressure force. Once again we have to be careful here. The right hand side in the integral energy balance equation we had net rate of work done on the fluid, and we said this term represents work done on the fluid and this term represents work done by the fluid. So, that is why this is positive and this is negative. This should also be kept in mind. This convention is in line with the rate of work done term on the right hand side. In the integral energy balance we said W dot net in, what does it represent? Net rate of work done on the fluid, that is why we have on the fluid and then minus by the fluid. Okay. That should be kept in mind. This is similar to the net rate of heat input term where we took in minus out. For the convection term it is out minus in. So, this difference has to be kept in mind. Just to summarize, for the convection term it is out minus in, for the heat term it is in minus out, for the work term it is work done on the fluid minus work done by the fluid. Okay. So, this has to be kept in mind in line with, that is how we started with the first law of thermodynamics. Okay. So, that should be consistently maintained throughout all the derivations. Okay. So, the net rate of work done by pressure force in the x direction, of course, we are discussing only the x direction, on the fluid is whatever done on the fluid minus whatever done by the fluid. Okay. Now, I would like to discuss this slide. What is shown in this slide are 2 different representations of the rate of work done terms. Okay. Usually control volume showing rate of work done is not available in most of the books. It is represented in few books, but the 2 different representations are followed in the books. Okay. So, what we are going to discuss is nothing conceptually new, but we have followed one way of representing the rate of work done terms. We are discussing 2 representations. Okay. Okay. The right hand side is what we have used, which we have discussed so far in the previous slide. How was this shown? See, rate of work done on the fluid is shown as an arrow mark entering in. So, that represents work done on the fluid. The right hand side, work done by the fluid is shown by an arrow mark leaving. So, similarly in other directions. So, left hand side entering arrow mark shows that work is done on the fluid, right hand side arrow mark shows work done by the fluid. So, it is shown as if something entering, something leaving, and similarly other directions. So, and we also interpreted this similar to the convection term, something entering, something leaving, flow entering, flow leaving. Similarly, we also interpreted the heat input term, heat entering and leaving. This is the convention which we have followed. Now, there is other way of representing the rate of work done by pressure force, and that is what is shown in the left hand side. The way in which this is shown is, remember, look at this, the terms are same, P multiplied by velocity in the respective directions, but look at the arrow marks here, they are drawn same as the pressure force itself. The 2 arrow marks are towards each other in the respective directions. What we have used is arrow mark entering and leaving. Left hand side convention is that the rate of work done terms are shown as 2 arrow marks towards each other. How do we interpret this? Now, this we should interpret as something similar to force. If you have a arrow mark in the positive direction, that is positive work, which means work is done on the fluid. If you have arrow mark in the negative direction, that is negative work is done by the fluid. So, when we draw a control volume with rate of work done terms like in the left hand side, then the interpretation is like a force. Right hand side, if you draw, then the interpretation is like the convection terms. So, we have chosen the right hand side, but few books, very few books which give this, some books may show the left hand side representation. So, because it is not available in many books, I thought I will discuss this, so that becomes clear how do you represent the rate of work done in terms of a control volume. Of course, we can mathematically do it as well without the control volume also, taking dot product of force due to pressure with velocity. That is what essentially we have done. Okay, so let us repeat it for all the three directions. So, net rate of work done by pressure force on the fluid in x, y, z directions. Okay, just repeat it for all the three directions and then divide by delta x, delta y, delta z. Okay. Okay. This is what we have discussed in the previous slides. Similarly, y direction, similarly z direction. Okay, let us divide by delta x, delta y, delta z and keep it ready for substitution. And at this stage they represent rate of work done, net rate of work done on the fluid, and moment you divide by delta x, delta y, delta z, they represent net rate of work done on the fluid per unit volume, taking care of all the three directions. So, now it is time to put them all together. Okay. All the control volumes are shown here. This control volume is for convection and of course, for the transient term also. This control volume is for the heat input term and this control volume is for the work done term. Okay. Of course, rate of heat input, rate of work done. Okay. What is that we are going to do now? This is the integral form of energy balance equation. We have got expressions for these four terms separately. Now, we are going to put them all together. Okay. So, let us remember, after dividing by delta x, delta y, delta z, we have already divided by delta x, delta y, delta z. So, the terms which are substituting here are after dividing by delta x, delta y, delta z.
Control volume, first term.
So, those are the left hand side terms which you have got earlier, that is a transient term. All these three terms put together convection, all these three terms put together represent convection. These three terms put together represent heat input. And these three terms represent the work done term. Okay. Now, we shrink the control volume to a point. So, as we have discussed earlier, at this stage all of them represent average values. Okay. when we write this term, rho and E are some average value within the control volume. When we write all these three terms, they represent average values over the phases. Okay. When we shrink, all of them become point values. So, delta x tending to 0, delta y tending to 0, delta z tending to 0. So, now they become instantaneous values and point values as well. So, this becomes dou by dou x of rho V x E, this becomes dou by dou x of rho V x E, and then this becomes dou by dou y of rho V by E, similarly z direction. And coming to the heat input terms, remember q x at x minus q x at x plus delta x. So, we have minus dou q x by dou x, that has to be kept in mind. This is what I have been repeatedly telling. For the convection term, it is outflow minus inflow. For the heat input term, it is input minus output, okay, heat input minus heat output. So, that is why we have q x at x minus q x at x plus delta x. So, when you take the limit, you have minus dou q x by dou x, similarly y direction, similarly z direction. Similarly, for the rate of work done, we have rate of work done on the fluid and then minus rate of work done by the fluid, because here we have W dot net in, meaning it represents net rate of work done on the fluid, and that is why if you take once again limit delta x tending to 0, you get minus dou p V x by dou x. So, this has to be kept in mind, so that we do not miss out on the sign. Left hand side we have positive derivatives, right hand side we have negative derivatives. Okay. So, this has to be kept in mind, and we have got the differential form of energy balance equation in terms of total energy. As we said, the energy balance derivation goes through a series of stages. What differs is the variable for which we write the energy balance for. So, now we have derived the energy balance equation in terms of total energy, which means left hand side we have total energy, of course right hand side we have the heat input terms and then the work done terms. Okay, now let us look at the significance of each term formally. We have, of course, we know the significance, we have been using it. I would not say I have used the formal terms every time for the purpose of brevity, but now it is time to put them very formally. Okay. Once you know the significance, we can easily understand the terms as well. Okay. Left hand side, this term represents time rate of change of total energy per unit volume. Okay. We have been using very formally time rate of change of total energy, and because we have rho into E, it is per unit volume. Okay. And of course, we know that in a differential balance equation all terms are per unit volume basis. Okay. What does the next set of three terms put together represent? Net rate of flow of total energy out by convection per unit volume. Okay. So, tells about flow of flow of which quantity? Total energy, and because energy can flow in and out, it represents net rate of flow of total energy out. What is the mechanism? By convection, and it is per unit volume basis. Right hand side we have net rate of heat input or heat addition by conduction per unit volume. Okay, that is a correct way of representing this term. It is represents heat input or heat addition. What is the mode? By conduction. It is net rate because it could be heat addition or removal, and so net rate of heat addition by conduction, of course, per unit volume. And what is the last term represent? Net rate of work done on the fluid, okay, by pressure forces per unit volume. Okay. So, it represents work done, is it on the fluid by pressure forces, okay, and it represents rate of work done, okay, and it is net rate, of course, per unit volume. So, every word there has a meaning. Rate of work done, it is net rate, it is on the fluid by pressure forces per unit volume. Okay. So, I would say a very precise way of writing the significance of the different terms in the differential total energy balance equation. Okay. So, now it is time to quickly compare the three differential balance equations which are derived. So, let us list down them first: the differential total mass balance equation, the differential linear momentum balance equation, and the equation which is just now derived, namely the differential total energy balance equation. Let us quickly compare them. The left hand side we have the transient term, which represents time rate of change of be it mass, momentum or energy. When I say momentum, it is x momentum, when I say energy, it is total energy. Then we have the transport of property by convection, that is represented by these three terms. What is transported? It could be mass, x momentum or energy. So, one is a transient term, other is a convection term in short. Right hand side, of course, for mass balance it is 0. For momentum balance, I have used the transport phenomena convention or the momentum transport convention, that is why we have a negative sign here. Okay. If we are following a fluid mechanics convention, it would have been positive, which means that tau xx, tau yx, etc. represent components of the molecular momentum flux tensor. And what does it represent? It represents transport of momentum by molecular transport. Okay. Here the left hand side represents transport of momentum by convection, right hand side we have transport of momentum by molecular mechanism. Okay. And we look at the energy balance, once again this represents the transport of energy by molecular mechanism, which is nothing but heat. Okay. So, here represents transport of momentum by molecular mechanism. The corresponding term, the analogous term in the energy balance is transport of energy by molecular mechanism. So, left hand side we have convection, right hand side we have molecular transport. Similarly, in the energy balance also left hand side convection, right hand side molecular transport. Okay, now let us look at the other terms. Of course, we have the surface force due to pressure and then body force due to gravity in the right hand side of linear momentum balance equation, and then in the energy balance equation we have the rate of work done term. Okay. Of course, that represents on the fluid. Okay. Also like to mention, when you compare these two equations, these two terms are analogous to each other, they represent transport by molecular mechanism. Now, the work done by pressure is represented by this term. Coming to gravity, the work done by gravity is on the left hand side, we will discuss that later. Okay. It is included in E as potential energy, we will discuss that in detail later. What is missing on the right hand side is the work done by viscous stresses, because we have neglected it. Okay. So, like to repeat it again, these two terms are analogous. Work done by pressure is here, work done by gravity force is included as potential energy on the left hand side, which we will discuss later. We do not have one term corresponding to work done by viscous stresses, if you interpret that as viscous stresses, and that is not there because we have neglected rate of work done by viscous stresses. Okay. So, that is how we should understand this. A more formal derivation, if you look at typical transfer phenomena book, will also include rate of work done by viscous stresses. To our level we are neglecting it, and is not a major limitation because the differential energy balance equation without the viscous stresses is applicable to almost, I would say, majority of the cases. Majority of the cases, you can say 95 to 99% we can use that. Okay.